I'm going to talk about partial weight exchange in federated learning. So here's the agenda of my presentation. I'm going to first give a brief introduction to federated learning, and then I'm going to explain the partial weight exchange algorithm, and then I'm going to show you some experiment results that we ran and mention some future work we hope to do. So let's start with what federated learning is. So federated learning is a technique where distributed clients want to collaboratively train a model without sharing their private data. So the setting you should consider is where your training data is distributed across different parties, which we call clients, like these three. And we want to leverage all of these information to train a single model without having to collect the data into one place. So this is achieved by the clients sending model parameters to the server, which is the central party which is going to aggregate the parameters instead of sending the data. So here is the most basic algorithm in federated learning called federated averaging. The basic step is like a global model is initialized on the server side. The server then sends the global model parameter to the clients. Clients perform local training and then send local parameters to the server to be aggregated. And we just repeat these few steps for several rounds. So here the arrows just represent the communication of the model parameters between clients and the server. So federated averaging basically means that the aggregation in this step is simply weighted averaging, where the weights are determined by how much data each client has. So given that basic setting, we have several challenges. The first is the heterogeneity of client data distributions. All this means is that because the data is distributed, the data held by different clients might be very distinct, and this might have negative impacts on model performance and conversion. The second challenge is the high communication costs between clients and server, which is particularly pronounced if your model size is very large. And the third one is privacy. And there are many different challenges, but in our project, we're going to focus more on the first two. Okay, so now I'm going to introduce you to the partial weight exchange regime that we considered. So if you recall, federated averaging by default exchanges the entire model between clients and the server. This might be undesirable if the model size is large, because then you incur a lot of communication costs. So partial weight exchange, as the name suggests, means that instead of exchanging the entire model, we only want to exchange certain parts of it. And any such idea has to consider two problems. First is how do we select which weights to exchange? And the second is how much do we exchange? And so some researchers at Amazon proposed that we can select the weights based on how much their magnitude change during training. So I'll make this a bit more precise. Well, this is the paper in which they proposed this idea. So they empirically observed that after each round of local training, most of the weights don't change too much in terms of its magnitude. So recall in federated learning, every client, they perform a certain epoch of local training before sending the parameters to the server. And what they have observed is that after local training, most of the weights don't change too much in terms of magnitude. However, there are weights that change a lot. So they hypothesize that those are the weights that are responsible for out-of-domain knowledge. And what do I mean by out-of-domain knowledge? Remember that in federated learning, we really want to leverage the information that's contained in all of those data and combine them together to train a global model. So out-of-domain knowledge just means knowledge that is very specific to the training data that's held by each specific client. So if we operate on this hypothesis, then it makes sense to only exchange the weights that change a lot in terms of magnitude throughout training. So that's the basic idea behind the algorithm. And in this project, we basically built a partial weight exchange system based on this idea and conducted its experiments to investigate its utility. Okay, so I'm going to get into a bit more detail in how the selection mechanism works. works. Here is the mathematical detail. Suppose we have a real number between 0 and 1, and suppose our model is a neural network with capital M tensors in total. Then what we're going to do is for every tensor, we're going to calculate how much its norm has changed in each local training round and select the top P times M tensors that have the largest norm change. So this is kind of technical, but for the purpose of this presentation, you can think of P equals 0.1 roughly as meaning we only exchange 10% of the model parameters, and which 10%? The 10% that have the largest norm change. And P equals 0.2 means that we only exchange 20% of the parameters and so on. Although this is not exactly correct because different tensors have different number of parameters, but for our purpose, you can hold this image in your mind. And another thing I want to mention is that since each client can now exchange different tensors, the aggregation on the server side is performed separately on each tensor. Okay, so this is the selection mechanism. Now I'm going to show you some experiment results. But before that, I'm going to explain the experiment setup. So we fine-tuned a Roberta-based encoder on the task of text classification. We used like a pretty canonical data set, AG News. And because in federated learning, we often encounter situations in which the data distributions across clients are very different, we used a Dirichlet sampling technique to sort of model this heterogeneous distribution setting. So all this means is that the number of data points in different classes are very imbalanced for each client, and then their data sets are also pretty distinct across different clients. And for us, we considered 3 different levels of data heterogeneity, which is quantified by a beta parameter. I'll get into a bit more detail in this later. And we considered 10 different exchange percentages, so all the way from 10% to 100%. I just want to point out that P equals 1.0 is equivalent to federated averaging because we're exchanging 100% of the parameters. And then we basically measure the test accuracy after federated training on the balanced test set. Okay, so that's basically the experiment setup. And for our purpose, we considered 3 different levels of heterogeneity, but you just have to realize that the smaller beta is, the more heterogeneous the data is. Like how that is done is sort of like some technical detail, which you don't have to worry about here. Okay, so given that setup, I'm going to show you some experiment results. The first is when beta is 1.0, which is the case when the data is the least heterogeneous. And in this case, the first observation is that we can, okay, on the x-axis is the 10 exchange percentage rates, so all the way from 10% to 100%. On the y-axis is the final test accuracy that's obtained. And the first observation is that when beta is 1.0, we can really reduce the communication cost by a lot without harming model accuracy too much, right? Like for example, when we only exchange 70% of the parameters, we get 93% accuracy, which is not that bad. And the second thing that I observed is that the worst exchange percentage in terms of performance actually occurs somewhere in the middle. So on the 2 extremes, if you exchange very few parameters, or you exchange all the parameters, in both cases the performance is sort of okay, but in the middle is the worst, which is a curious phenomenon. And here is the case when beta is 0.5. So in this case, we can see that well, partial weight exchange suffers a bit more in terms of model performance because now the data is more heterogeneous. But there's still a lot of room for reducing communication costs. Like, for example, 70% exchange rate still performs pretty good. However, we also observe that the worst exchange percentages occur in the middle. And that's not exactly the same as the first one, but it is a pattern. And finally, it's the case when beta is 0.25, so the case when the data is the most heterogeneous. And in this case, we can see that partial exchange doesn't work very well. If we don't exchange the full model, the performance is pretty bad compared to full exchange. But again, we see this curious trend that the worst exchange percentages are sort of in the middle. And so I guess the conclusion is that as long as the data is not too heterogeneous, it seems like we have a lot of room of reducing communication costs without having to exchange the entire model. And then some future work we want to do is to evaluate the system on like more data sets, maybe on a more realistic medical data sets such as Gemini. We also want to explore more why the worst exchange rate occurs in the middle. And we also want to consider more generic selection mechanisms that go beyond just selecting tensors, because right now we only exchange individual tensors. And maybe we want to explore like a sparsity approach in the future. Yeah, that's all. Thank you. I'll be happy to take any questions.
Yeah. First of all, great presentation. I believe it has a lot of practical applications. I just have a few questions. One of them is related to the way the criteria you mentioned norm change to select weights. Is there any other criteria besides that, or have you tried it?
So in the original paper, they actually proposed like an opposite criteria in the sense that you can exchange the weights that change the least. Yeah, and in terms of other criteria, well, you have to sort of measure the weights in some way. So in general, you can consider any function that takes in the weights and outputs some kind of real number. And if you take any kind of thresholding, you can use that as your selection criteria. I think we considered magnitude because there's this sort of natural interpretation that if we obtained a lot of information, that should be reflected in the change of magnitude. Yeah, but in our case, we only considered that, but there's definitely more possibilities out there.
And when you were just showing the experimental results, we saw, for example, if you exchange 10%, it's higher than like half of the weight, right? So I know it's experimental results, and like most of the aspects of deep learning, you may not know why it's happening, but do you have any intuition? What do you think?
You mean like why the worst?
Yeah.
In the middle?
If you exchange all the weights, it's higher. And if you exchange, for example, 10%, it's higher than if you exchange, for example, 40%.
Mm-hmm. Yeah, so there, I don't have like a very good answer to that because we didn't have the chance to investigate this too deeply. But one possibility is that, so this is not the first situation in which such dynamics is observed, right? Like, I think it's in like layer norm or batch norm, perhaps. Like in one of those cases, you can look at the threshold. You also observe that it's somewhere in the middle that have the worst performance. I think it's dropout. Sorry, the dropout rate. Yeah, so it might be something similar to that. I'm not too sure.
Great. Thank you.
Yeah, of course.
Great presentation. I have a question. You mentioned that you'll be using potentially Gemini, applying it to the Gemini data set. What task would that be for that particular data set?
You mean like what task or? Like
what machine learning task? Would you be like predicting sepsis or like, do you know what they'll do?
So, the thing is that our way of measuring heterogeneity is really like based on labels, right? It's kind of like the way we measure heterogeneity is to see how imbalanced the data set is. So I think as long as it's some kind of classification task, maybe like, binary classification, like in the case of medical data sets, or, with more classes, that as long as it's some kind of classification task, then we should be able to apply the same approach. If it's not classification, then it might be harder to quantify the heterogeneity of the data set. Yeah, so I would say like maybe the first natural extension is to consider classification tasks.
Great, thank you.